Hello, my name is Farouk Mahmood, and this is my project presentation for the class Deep Learning for Data Science. I'll be presenting the results of my deep learning project where I reproduced the GoogleNet model, which was introduced by Szegedi, I have no idea if I'm saying that right, and others in their 2015 paper, Going Deeper with Convolutions. I'll go through the motivation, model structure, my implementation, results, and final reflections on the project. The paper Going Deeper with Convolutions has 9 authors. For the remainder of this presentation, I will refer to Going Deeper with Convolutions simply as the Szegedi paper. In the field of computer vision, convolutional neural networks have made significant strides, especially in image classification. The inception architecture introduced in the Szegedi paper was particularly innovative because it managed to balance computational efficiency with increased depth, helping it to win the 2014 ImageNet challenge. My project was motivated by a desire to reproduce GoogleNet using TensorFlow and test its performance on both ImageNet and the SAFAR10 dataset. ImageNet is a large-scale dataset with over 1 million images and 1,000 classes, widely used for training CNNs. However, due to computational constraints, I used a subset of 14,738 images mapped to the 10 classes found in the SAFAR10 dataset. These images were then downscaled to 224 by 224 pixels, the same size Szegedi used. SAFAR10, on the other hand, consists of 60,000 images in 10 classes, but at much lower resolutions of 32 by 32 pixels. For consistency, I upscaled the SAFAR10 images to 224 by 224 during training. GoogleNet's architecture is built around inception modules that perform convolutions in parallel using different filter sizes, 1 by 1, 3 by 3, and 5 by 5, along with max pooling. These branches are then concatenated to capture features at multiple scales. A key innovation was the use of 1 by 1 convolutions for dimensionality reduction, which helped reduce computational costs while allowing the network to be deeper. In my implementation, I used the Atom Optimizer with a learning rate of 0.0001 to train the model. Here is a visual depiction of the GoogleNet architecture. The input image is a 224 by 224 pixel RGB image, which is shown here in this gray input box in the top right, which is then given to a 2 by 2 convolution of stride 2. This is this orange box. Then there's a max pooling layer, this green box. Then a 2 by 2 convolution layer of stride 1, followed by a max pooling layer right here. Up until this paper, sequential architectures, like the first part of the diagram, was the prevailing architecture. While Szegedi and team got novel was in the inception module. And this is this group of convolutions and max pooling and concatenation layers here that I'm circling with my mouse. You can tell it's an inception module because it has branches and parallel convolutions. Then the outputs of these convolutions are combined in this concatenate layer, the green box. This allows the network to capture features at multiple scales simultaneously. And then we have a second convolutional layer here, and so on and so on and so on. This approach enables the network to learn more complex spatial hierarchies from the input image compared to traditional sequential architectures, which only process features one layer at a time. The key innovation of the inception module lies in its use of 1 by 1 convolutions for dimensionality reduction before applying the larger 3 by 3 and 5 by 5 convolutions. This helps reduce the computational costs while maintaining high accuracy. After multiple inception modules, we move to global average pooling, this blue box, which reduces the feature maps to a single 1 by 1 output per feature map before the final fully connected layer for classification, which is this dense layer here. This combination of deep and wide architecture allowed GoogleNet to outperform previous models and win the 2014 ImageNet challenge. For the code, I used TensorFlow as the framework and found some inspiration from GitHub and the TensorFlow documentation for the inception module implementation. Fortunately, the Szigeti paper well documented the specifications of the inception modules, and so it was pretty easy to convert that spec in the document to Python TensorFlow code. I also relied on blog posts for guidance on data augmentation techniques. One of the main challenges I faced was implementing the branching and joining structures of the inception modules, which are more complex than the simple sequential networks I learned in class. I also had to reduce the batch size due to the constraints of running on a desktop PC. My PC does have a GPU, albeit not one tuned for machine learning workloads, only 5 gigabytes of dedicated memory. I found that with a batch size of more than 16, I was getting out-of-memory errors in my GPU. And to avoid overfitting, I incorporated data augmentation techniques. Before diving into the complexity of the GoogleNet architecture, I implemented a simple sequential model as a baseline. Sequential models are straightforward. Layers are stacked one after another without any branching. My model started with several convolutional layers, followed by max pooling layers to reduce dimensionality, and ended with fully connected layers for classification. This is a traditional architecture that was popular before the introduction of more advanced modules like Inception. I use this model to serve as a comparison point for the more complex GoogleNet structure. While effective, the sequential model is limited in its ability to capture multi-scale features compared to GoogleNet's parallel branches. Here is a visual depiction of the simple model I used for comparison. This is basically the GoogleNet architecture without the Inception modules. In here I'm showing you a table taken out of the Szigeti paper, which gives the specification of the GoogleNet architecture with the Inception layers. So you can see here the first layer is a convolutional layer of size 7 by 7, and it tells you the output size as well as the depth. Followed by a max pool, then another convolution, followed by a max pool, and then there's the inception layers right here. So what I did for my simple model was start out with these first 4, and then added some more layers, and then eventually did an average pool, a dropout, and then a softmax layer at the end, just to see what the performance would be like in comparison to the real network here, which is given by this table. So my replication of GoogleNet produced some promising results. On a subset of ImageNet images, I achieved an accuracy of 66.2% compared to 58.1% with the simple model. However, on the Safar 10 dataset, the results were less impressive, only 22.6% for GoogleNet compared to 21.4% for my simple model. I think the smaller dataset size and the lower resolution of the Safar 10 images caused the model to miss some important features. Additionally, my accuracy was lower than the original papers, likely due to these constraints and the smaller scale of the experiment. The Szigeti paper used the top 5 error rate as the accuracy metric. They achieved a top 5 error rate of 6.7%, which was better than previous ImageNet challenge winners. I didn't find that metric useful, however, primarily because I only had 10 classes and not the 1,000 classes in the original ImageNet dataset. Therefore, I used the accuracy metric in TensorFlow. I believe this to be a more effective metric to evaluate the model's performance within the constraints of a smaller dataset and fewer classes, providing a clearer picture of how well the model generalizes to unseen images. Since the publication of the Szigeti paper, many innovations have been made, like MobileNet, which are optimized for mobile and resource-constrained environments. The fact that you can do image recognition tasks on mobile devices now is possible in part because of Szigeti and team's work. This project gave me valuable hands-on experience in writing TensorFlow code for a complex CNN architecture. In the future, I could improve performance by using a larger dataset. I would also explore making the network implementation more dynamic so that it can process both ImageNet and Safar 10 images with around the same level of accuracy. This class, although short, helped me understand neural network fundamentals. They are definitely less intimidating now that I've gone through the class. I am eager to continue expanding on this project at UWF and in my professional career. This concludes my presentation. Thank you for watching.